All right, so let's see what we're doing today. Let's go back to Moodle. Oh, no. All right, let's see if we had any announcements. Oh yeah, the second midterm. That's right. I thought so. That should be ready by tonight at midnight. Okay, that's what I kind of figured. So tonight is the night you should have your second midterm ready. That, remember, is all chapter 8. And then in the meantime, we're just go pick it up where we left off in chapter 11. So let's see, how far did we get? Here we go. We also, we should have at least a few more videos that we can watch. Last time we definitely watched the one with the lady tasting tea, and I think you probably had a good time with that. She showed them. She knew that she could definitely tell the difference between whether the tea was poured first or the milk. Everyone was skeptical, but she proved them all wrong, didn't she? So that was kind of fun. Let's see, what else do we have for us? Oh, okay. So let's see, there's at least 2, maybe 3 more good ones that we can look at today that are all related to probability theory. And one that will be very, very surprising to you. And as a matter of fact, I'll tell you what, this first one, I just noticed it sitting here, the check your intuition, the birthday problem. This is really more about combinations. So you know what, why don't we watch this one first? I think you'll find this to be extremely interesting because the results are so surprising. So, all right, let's just watch this one first, and then we'll go back to chapter 11. And it is directly related to what we were discussing with arrangements, combinations, and permutations. All right, so let me move it up the list here. I'll send you the link.
Whether you're building dynamic network models.
All right, let me send you okay, here it is. Okay, what's going on? I can't find the, oh, it's way down here, that's why. There we go, got moved down here somehow. All right, here we go, here's the chat. Let's check this out. It really is very interesting and surprising. All right.
Models are forecasting real-world behavior. Neo4j's new graph algorithms book will walk you through hands-on examples of how to use graph.
Imagine a group of people. How big do you think the group would have to be before there's more than a 50% chance that 2 people in the group have the same birthday? Assume for the sake of argument that there are no twins, that every birthday is equally likely, and ignore leap years. Take a moment to think about it. The answer may seem surprisingly low. In a group of 23 people, there's a 50.73% chance that 2 people will share the same birthday. But with 365 days in a year, how is it possible that you need such a small group to get even odds of a shared birthday? Why is our intuition so wrong? To figure out the answer, let's look at one way a mathematician might calculate the odds of a birthday match. We can use a field of mathematics known as combinatorics, which deals with the likelihoods of different combinations. The first step is to flip the problem. Trying to calculate the odds of a match directly is challenging because there are many ways you could get a birthday match in a group. Instead, it's easier to calculate the odds that everyone's birthday is different. How does that help? Either there's a birthday match in the group or there isn't. So the odds of a match and the odds of no match must add up to 100%. That means we can find the probability of a match by subtracting the probability of no match from 100. To calculate the odds of no match, start small. Calculate the odds that just one pair of people have different birthdays. One day of the year will be person A's birthday, which leaves only 364 possible birthdays for person B. The probability of different birthdays for A and B for any pair of people is 364 out of 365, about 0.997 or 99.7%, pretty high. Bring in person C. The probability that she has a unique birthday in this small group is 363 out of 365, because there are two birth dates already accounted for by A and B. D's odds will be 362 out of 365, and so on, all the way down to W's odds of 343 out of 365. Multiply all of those terms together, and you'll get the probability that no one shares a birthday. This works out to 0.4927. So there's a 49.27% chance that no one in the group of 23 people shares a birthday. When we subtract that from 100, we get a 50.73% chance of at least one birthday match, better than even odds. The key to such a high probability of a match in a relatively small group is the surprisingly large number of possible pairs. As a group grows, the number of possible combinations gets bigger much faster. A group of 5 people has 10 possible pairs. Each of the 5 people can be paired with any of the other 4. Half of those combinations are redundant because pairing person A with person B is the same as pairing B with A, so we divide by 2. By the same reasoning, a group of 10 people has 45 pairs, and a group of 23 has 253. The number of pairs grows quadratically, meaning it's proportional to the square of the number of people in the group. Unfortunately, our brains are notoriously bad at intuitively grasping nonlinear functions. So it seems improbable at first that 23 people could produce 253 possible pairs. Once our brains accept that, the birthday problem makes more sense. Every one of those 253 pairs is a chance for a birthday match. For the same reason, in a group of 70 people, there are 2,415 possible pairs, and the probability that 2 people have the same birthday is more than 99.9%. The birthday problem is just one example where math can show that things that seem impossible, like the same person winning the lottery twice, actually aren't unlikely at all. Sometimes coincidences aren't as coincidental as they seem.
So I imagine you found that surprising. You only need 23 people in the group to guarantee or to have a probability of at least 50% that 2 of them have the same birthday. Now, I do want to point out that they mean just the day and the month, not the year. But considering how many days there are in the year, I'm sure most people would be very surprised to hear that. But you can see it makes perfect sense when they explain it that way, because they're explaining it in terms of combinations, and which we've already seen. When he was talking about the number of pairs, with 5 people, there are 10 pairs. He was actually talking about combinations. So we've seen all of this before, but we never saw a fun application like this before. And it can produce some surprising results with these counting techniques. So that's one of the more amusing examples that we run across in math. And now you can save that as a surprise for whoever you want to impress by saying, you know, all we need is 23 people in the group to have at least or a 50% chance of 2 people with the same birthday. And they proved it to us. And in a very fun way, I must say. It was a very amusing video. So it was well worth our while to watch it and give us a sense of what kinds of problems can be solved with combinations, permutations, and arrangements. All right. Well, anyway, so, and of course, the lady with the T was also an interesting application. Ronald Fisher, of course, being who he was, he would be the first person to come up with an experiment to test the idea that she really could tell the difference between whether the tea was poured first or the milk was poured first. So by the way, all of this discussion we've had up to this point was part of a field of mathematics called combinatorics, which is basically the science of counting. Arrangements, permutations, combinations are all part of the field of combinatorics. And we see a lot of this in computer science and also in statistics and other applied fields as well. Okay, because it can be potentially extremely useful. But anyway, now we're going to move on to probability theory. And again, I think we may have started to look at this last time. What it does is it provides us with a mathematical framework for measuring uncertainty. And of course, there's a lot of uncertainty in the world, as you know, and what we're trying to do is come up with a way of assigning probabilities to unknown events. So we start out by assuming that some type of a process is taking place, which we will call the random experiment. Now, there's a lot of different things that can qualify as a random experiment. What's important, though, is that we need to have a process where all the possible outcomes are known in advance. But of course, the actual outcome is not known in advance. Otherwise, it would no longer be random. So when these conditions are met, it becomes very straightforward to assess or assign probabilities. So some simple examples of this are spinning roulette wheel, which, by the way, if you've never seen one, it has 38 numbers on the wheel, each of which is equally likely to turn up. Most of them are either red or black, but there's also 0 and 00, which are green. And the frequency of the numbers on the wheel determines how much you can win by betting on those numbers in a casino. Okay, so roulette is a gambling game, and it's very popular in American casinos, although it is a French game. It was invented in France, and you see a lot of times in movies, like with James Bond, for example, where he's gambling in Monte Carlo, they definitely have roulette in those casinos. It's a very old game, and it's very, very popular. Choosing a card from a deck, same thing. We know when you pick a card what the range of possibilities is. Well, of course, we don't know which one we'll actually pick. And when you roll a pair of dice, as you all know from experience playing games, the dice can come out with sums anywhere from 2 to 12. And by analyzing the dice, we can figure out the probability of any one of those numbers happening. For example, the chances of getting a 7 are 1 out of 6. The chances of getting a 2 are 1 out of 36. And we can prove that by writing out all the different combinations of dice that we can roll and just counting them up. Now, we're going to create a very simple example here. And what we're going to do is roll a die twice, but in such a way that we're only paying attention to whether it turns out to be evens or odds. The reason why we're doing it this way is because if you roll the dice and keep track of the actual numbers, you'll always have 36 possible outcomes, which is a lot. So instead, we're going to only keep track of evens and odds, which reduces the number of possibilities to just 4. And that will make things a little bit simpler for us. So what are those 4? Well, we can get an even followed by another even, an even followed by an odd followed by an even, and an odd followed by an odd. Now, I'd like to point out that because evens and odds are equally likely to turn up on a die, each of these outcomes is equally likely to occur. And since there are 4 of these, that implies that each one of these has a probability of 1 out of 4. Okay, so all of these outcomes, because they're equally likely and because there's 4 of them, each of them has a probability of occurring of 1 out of 4. All right. Oh, by the way, here's a fun note. In case you weren't aware of this, die is the singular, dice is the plural. Okay, it's, there's no such thing as dies. It's either die is one, dice is the other. Now, so the chances of getting an odd or an even on a single roll is, of course, a half, because each die has 6 different faces, 3 of which are odd, 1, 3, and 5, and 3 of which are even, 2, 4, and 6. Now, with 2 rolls, the number of possibilities is 4. And by the way, in case you're wondering, every time you roll the die, the dice, or sorry, one die, every time you roll it, the number of possible outcomes under these conditions will double. All right. If you roll the die and you're paying attention to the individual numbers, every time you roll it, the number of possible outcomes is multiplied by 6. All right. So in other words, if I roll the die 3 times and I'm only focusing on evens and odds, I'll end up with 8 possible outcomes. All right. And of course, in our case, we're only rolling the die twice. So there's only 4 possibilities, each of which is equally likely, which means that each one of them has a probability of 1/4. That's an important result because it'll help us with what's coming next. It doesn't have to work this way, by the way. All the results we're going to derive would work equally well if the outcomes weren't all equally likely. This just makes things a little bit simpler. All right, so from now on, we're going to abbreviate even and odd. Obviously, E is even, O is odd. And what I've got on the next slide is a tree or a diagram that will help you figure out what's going to happen or what could happen every time I roll the die. So if you can see what's going on here with these different branches, when I roll the die once, I'm only going to get either an even or an odd, each of which has a probability of 1/2. If I roll a second time, the number of possibilities doubles to 4. So I can get an even and an even, odd, odd, even, odd, odd. And because there's 4 of them, each of which is equally likely, each one must have a probability of 1/4 or 0.25. Then if I roll it again, there's now 8 possibilities. Remember, it doubles every time. And they're listed down here, ranging from 3 E's to 3 O's and everything in between. And because now there's 8 possibilities, each one must have a probability of 1/8 or 0.125. So clearly, if I roll the die a 4th time, there will be 16 possible outcomes, each of which has a probability of 1 out of 16. The 5th time, it goes up to 32. So in other words, it just keeps doubling every time. Well, we're only going to focus in this chapter on the second case where we have 4 outcomes, because we can derive all of our results very quickly and easily from that case. Now, we can, in probability theory, we have some special terminology, as you can probably imagine, like all areas of every discipline, math, computer science, biology, whatever, you name it, it has its own unique language. And so here we can think of a set that contains all the possible outcomes of our experiment. It will be from now on known as the sample space. You can see by these braces that it's a set. It's simply a collection of elements or objects. The order in which I write them is irrelevant. Okay. Now, before we go any further, I know for a fact that you've been exposed to set theory in your travels. What I'd like to do is review it with you just quickly enough, just a little bit, to remind you how this works so that what follows will make sense. All right, imagine I've created the sets A is 1, 2, 3, B is the set 2, 3, 4, C is the set 5, and D is the set 1 and 2. Now, you might remember this U symbol stands for union. And in set theory, the union operator means I'm taking 2 sets and simply combining them. It's just that simple. I'm taking whatever's in A and whatever's in B, and I'm putting them together into one big new set. And all it has in here is all the elements that are either in A or B or possibly both, because they could overlap. Okay, so 1, 2, 3, 4 is the union of A and B, because that contains all the unique elements in A and B. Now, in some books, union is replaced with the English word or. So it's possible you were exposed to it that way. A union B, A or B means the same thing, because it is a set that contains all the elements in A or B or possibly both. So that's a pretty easy idea. It's a very straightforward concept. Just put them together into one big new set. All right, so hopefully this is all coming back to you. you're saying to yourself right about now, oh, I remember seeing this stuff. Oh yeah, I remember now. So anyway, what's next? Now, we also have this other operator that applies to sets, which is called intersection. It's basically an upside down U. And what it represents is a new set that contains all the elements in these two sets. In other words, A intersect B is 2 because that's the only element that they have in common. All right. So A intersect B is 2, again, because it is the only element they have in common. And in terms of English, sometimes the intersection symbol is written as and. So when you see A and B, it means all the elements that are in both A and B. So here it's just the 2. Now, I would like to point out here that it's possible that there are no elements in common. In other words, let me sneak this one in here too. What about B and C? What elements do B and C have in common? Well, the answer is none. So in that case, you would say, remember, B is 2, 3, 4, and C is 5. The intersection between these two sets, well, there isn't one. There's no elements in common. We write this as the two braces with no elements in the sets. In other words, this is known as the empty set. This implies that B and C have no elements in common. And in terms of mathematical notation, this means that B and C are mutually exclusive, we call it. So imagine that instead B and C were the set of odd numbers and even numbers. Obviously, they have no elements in common. And so their intersection would be the empty set, or we could say that the odd numbers and the even numbers are mutually exclusive. It just means that they have no elements in common. All right. And I'm sure you can think of a lot of sets that have no elements in common. Now, in the next slide, I have another example of this. A and C also happen to have no elements in common. They're mutually exclusive. Oh, by the way, I almost forgot to mention this 0 with a slash through it. Some books use that to represent the empty set. You may have seen that as well. It means the same thing, right? It's simply another way of expressing the empty set. Oh, let me just quickly save this. We don't want to lose all my writing here. Today is the 8th. Okay. Now here's an interesting idea, this notion of subset. This, now it looks like, I know it looks like a C. It's hard to draw it without making it look like a C. Let me see if I can tighten this up a little. This symbol is read as subset. And so one set, let me put a definition up here. Set, let's say, set A, or let's just say set X, because I don't want you to think it's one of these. Set X is a subset of set Y if all elements of X belong to set Y. So for example, if X is 1 and 2, and Y is 1, 2, 3, 4, then X is a subset of Y, because all the elements in X belong to Y. Just like this class could be thought of as a subset of the entire student body at SUNY Purchase. Okay, you're all SUNY Purchase students, and you belong to the entire university or college, or the SUNY system too. You can think of it that way. SUNY Purchase is a subset of the entire SUNY system. So in other words, because it belongs to it. You know, you can make up a lot of examples, but the important idea is that whatever's in set X, all of those elements belong to set Y. So therefore, in this case, D is a subset of A, because as you can see, D contains the elements 1 and 2, whereas A contains the elements 1, 2, and 3. So all of D is in A. And therefore, D is a subset of A. So it's a pretty straightforward concept. Here's another one. Just you know, a practical example. A is all SUNY Purchase students. B is all the art majors at SUNY Purchase. Well, I think it's a pretty clear statement that B is a subset of A. Of course, the art majors are part of the entire student body. Now, you're probably wondering, what about cases where this isn't true? For example, let's go back to the sets we were just looking at. And what about C and D? Is C a subset of D? No, because 5 is not an element of D. So the symbol now has a big slash through it. Okay, so often in math, that big slash just means the opposite. So if this is the subset, this means not a subset. It's just like when you're ready to cross the street. Sometimes they used to have a big sign where there'd be a walking man there, and then they'd have a big circle and it would be a slash through it or something that meant don't walk. Or sometimes you see when you're not allowed to smoke in a building or whatever the place is, there'll be a picture of a cigarette with a big red circle and a big slash. And that's where that would have come from, because the slash has always been meant to represent, do the opposite of what the symbol says. So C is clearly not a subset of D, because C5 rather is not part of 1 and 2. Now, I just want to quickly also show you some very interesting graphs that you may have encountered that help us understand these relationships, I guess. We have this very special type of graph which is called a Venn diagram. And what it's designed to do is help us understand the relationship between sets. So imagine this is A and this is B. What I'd like to do is show you that the union of A and B is this shaded region. Because every element in A and B is combined into a single new set. At the same time, though, the overlapping between them is called the intersection. Okay, now I don't know if that helps you or not visualize what's going on, but these are traditionally used to help us understand the relationship between sets. The whole box is often referred to as either the sample space or sometimes the universal set, meaning all the elements that potentially could be contained in A and B. Okay, so you may have learned this as you use the universal set, if you've seen this before, and it could also mean the sample space. They are the same idea. All right, now, what else can we do with this? I'd like you to see this important relationship. Suppose A and B have no elements in common. Okay, the intersection between A and B is the empty set. They have nothing in common. Okay, A and B are mutually exclusive. And one more thing I'd like you to show you with the Venn diagrams is the concept of subset. This is what it means to be a subset. So in this case, B is a subset of A. Because B is contained within A. Just like my example of the art majors at SUNY Purchase and the entire student body, the art majors would be B and A would be the entire student body. All right, so those Venn diagrams are very helpful. And if you think about it, if you don't recognize them, well, think about it a little longer. I would be willing to bet that you've seen them somewhere along the way. It's possible you haven't thought about them in a long time, but I'm pretty confident you've seen them before. Your memories are, as we speak, your memories are searching for this stuff. And sooner or later you'll say, oh, that's right. I remember learning about this in old Mrs. Smith's class. And yes, so that was meant to illustrate what's happening. Now, we're going to define a new key term here called an event. And it's the events that we're really interested in because we're going to calculate probabilities for these events. An event is a subset of the entire sample space. You can see why all this background was necessary so we can understand what this actually means. So remember, S arises when we roll a die twice and we only pay attention to evens and odds. What if we are playing some kind of a game in a casino where our prize depends on this happening? At most, one even number turns up, which basically means everything but two evens. If we get two evens, we lose. But if we get anything else, we win a prize. So we'd like to know what is the probability of this actually happening. So the first thing we want to do is write out F itself. And you can see it is itself simply a set that contains elements from the sample space, defined by this phrase, at most one even number turns up. Okay. So how would that work? Now, remember, we mentioned earlier, there's actually a couple ways we can do this. We mentioned earlier that each of these outcomes in the sample space is equally likely to occur. So here's what we can do. Each one of these has a probability of 1/4, as we discussed. So here's what we can do. Since F contains EO, OE, and OO, why don't we just combine the probabilities of those three outcomes? Okay. So let's do that. On the next slide, that's exactly what we're going to do. So remember, each one of these, we've defined it as being equally likely. So that makes things a lot simpler for us because the probability of F is equal to the probability of getting EO or OE or OO. And since each one of these has a probability of 3/4, we simply add them up and we get either 0.75 or 3/4. Now, this approach always works. Whether the outcomes are equally likely or not, this always works. What I'm about to show you in the next slide is a shortcut that only works when all the outcomes are equally likely. It can speed things up, but again, it only works when all the outcomes are equally likely. All right, so let's take a look at the special case. We're literally just going to take the number of elements in our event and divide by the number of elements in the sample space. Okay, so if all sample space elements, which by the way are often called sample points, are equally likely, then this is true. All we need is the number of elements in E, sum of NE versus the entire sample space, and we're good. So in our example, we could just write it like this. How many elements are there in F? How many elements are in the sample space? The ratio is 3/4 or 0.75. And it's the same answer. But again, you should only use this when the outcomes are equally likely in the sample space. All right. So this means that if whatever this game is, I've got a 3/4 chance of 75% chance or 3/4 chance of winning. All right, now, what about this case? Now, here's a more complicated version of what we just did. I went ahead and showed you here. Now, this shows you the sample space is what happens when you have roll the die 3 times. And so you can see there's 8 equally likely outcomes. And I've defined the event A to represent we got at least 2 even numbers. And so what I did was I went through and I looked at them all. I said, you know, that only happens on the top row here. EEE, EEO, EOE, OEE. So now, how do I calculate the probability of A? Well, because these are all equally likely in the sample space, all I have to do is count 4 elements in A divided by 8 elements in the sample space, which gives me 4 out of 8 or 0.5. In fact, you know what I'd like to do? Let me add one more step to this. First, let me give you a minute to catch up, but I'd like to show you an alternative way of doing this. All right, so just be aware that each of these individual outcomes, when we have 8 equally likely outcomes, each one of them has a probability of 1/8. All right, so remember, A equals triple E, EEO, EOE, OEE. And each one of these, because each element in the sample space is equally likely and the sample space contains 8 elements, it must be true that the probability of each of these outcomes is an eighth. And so therefore, the probability of this event A is the sum of these 4. I'm running out of space here, so I'll have to move it to the next slide. But the probability of A would simply be the probability of each of these added up, which of course is going to end up giving us 4/8 or 1/2. So let me just add that to the next slide. So we have triple E plus EEO plus OEOE plus OEE. Four eighths, or of course 1/2. And that's exactly what we had before. Okay, now what I've got here is another example where the sample space has elements that are not equally likely. I want you to see one example where they're not all equally likely. Okay, so we're playing a game now where there's a special pair of dice. These are not normal dice. In these dice, there's only 2 evens and 4 odds. Well, here's the thing. Each of these is different now. So we've got still the 4 possible outcomes, but they're not equally likely to occur. All right, now in the next slide, I have a chart showing you what the actual probabilities are. And then when we got them put together, we can calculate probabilities based on them not being the same, okay? So yeah, these are very strange dice, but this is a special game of some kind that's played in the casino where you've got, I don't know, like 2, 4, 7, 9, 11, and 13 for something like that. So anyway, so when you've got a setup like this, the chances of getting an even is only 1/3, and the chances of getting an odd is 2/3. So that when you roll the die a second time, the chances of getting 2 consecutive evens is 1/3 times 1/3, which is a ninth. EO is 1/3 times 2/3, which is 2/9. OE is 2/3 times 1/3, which is 2/9. And then finally, OO would be 2/3 times 2/3, which is 4/9. Now, all of these do add up to 9/9. So that's fine. But you can see before they were all equal to 1/4. So now when we calculate probabilities, the only option we have is to add up the individual elements because they're all different. Okay. So again, let me give you a minute to catch up, and then we'll do a couple of examples and you'll see how this is, it's just a little different. It really, the only way it's different is that you lose the ability to simply count how many elements are in your set compared to the sample space. Here, you're just basically combining all the individual probabilities. All right, so are we ready? All right, let's give it a minute. So imagine now we define an event. This is the same one. I think this is the same one we had before, wasn't it? Hold on. Yes. So once again, we're going to use F to represent at most one even turns up. Now, of course, that means everything except two evens. But before we calculated, we ended up with a different result. So if we still have F representing at most one even turns up, or EO, OE, and OO. So if you notice, this time, the only way we can do this is to add up the three individual probabilities, and we end up with 8/9, okay? Because they're not all the same. Instead of 3/4, we ended up with 8/9. And we can't use, this is just as an aside, since the probabilities are not equal, we can't use the number of F divided by the number of S. Okay, because that's not going to give us the right answer. Okay, we have to do it this way. All right, now we're ready to move on. Now, oh, hold on. Let me look and see if we got more fun videos. What we're going to do now is define a series of rules that will enable us to calculate probabilities for more complex events, where we are basically taking a function of these individual events and doing some arrangement to them, or combination, or we're applying some algebraic operations. But before we do that, I think we do have a couple more videos that we should look at. Here's one called probability. Yeah, I want you to see this one. It's just called probability part 1, but it's a very good overview of what we've been doing.
Looking for dinner made easy?
So I'm going to send that to you right now. And let's look at this before we go any further. Okay, what's going on here? I can't find the... Oh, no. Now, this has been happening quite regularly this semester. Is this stuff here, or isn't it? I think the recording, oh, for God's sake, I think the recording might have stopped. I'm not seeing the instructions. Hold on. Yeah, well, what else is new? So I think, God, what are we doing here? This part is still on though. Why? How is this? You can see something's wrong. It's just not cooperating at all. It's really annoying. I don't know how to turn it off. I have a feeling, I mean, it's probably, it stopped for some reason. Now, the last several times we were able to get it going again. Yeah, this is really annoying. Yeah, the meeting controls are completely messed up. I'm trying to figure out the most painless way of getting this started up again. We'll start by hitting quit Zoom. It's not even working. Unbelievable. I just want to see if it made the recording or not. Well, it seems to think. Yeah, that tells me that it stopped. All right, you know what? Let's do this. Uh, Can't even get this thing to stop. I mean, it will, it's just completely stuck. I don't know if there's any way. I'm trying to quit Zoom and start it all over again. Oh, it doesn't. Jesus. All right, Alt F4. Let's see. What do you think the odds are of that working? I'm going to say 0. No, of course not. Well, you know what? I'll figure this out later. I don't know if I can even show a video now. All right, I'll tell you what, let's try this. Let's just carry on with the rules and just go as far as we can. And I'll deal with this piece of crap later on. All right, we don't want to waste any more time with this thing. So, all right, so here's the rules that I want to look at. This is technology at its finest, I have to tell you. It's just unbelievable how few things actually work the way they're supposed to. But anyway, so we've got the three rules: the addition rule, the complement rule, and the multiplication rule. By the way, is anyone still out there? Can you actually hear this or see this?
We can hear you.
Okay, well, that will have to suffice for today. Oh, wait a minute. What happened here? All of a sudden I see it again. It says you are screen sharing. Maybe if I stop share. No, it's just completely, there's just something horribly wrong with it. So, all right, we'll just carry on for a while and we'll try to get it fixed for next time. Jesus, just unbelievable. All right, well, then there's three rules. And they are the addition rule, the complement rule, and the multiplication rule, as you can see. The first one is pretty straightforward. The addition rule tells us what to do in cases where we have a union of two events. All right, so these are two events. We're trying to combine these and calculate the joint probability of these two, but the rule might surprise you a little bit. And you can see that what you're being asked to do is add together the probabilities of A and B, but then we're being asked to subtract the probability of their intersection. So basically, I mean, it's a simple rule. The question is, why is this happening? Well, first, let's look at a couple of examples and we'll see how this works. So let's just say that we're going back to that experiment with the die that we rolled twice. So our sample space is E, EO, OE, and OO. A represents the event that the first roll is even. So we can define that very easily right here. That would be EE or EO. The first roll is even. B, exactly one roll is odd. Either we're going to get EO or OE. Because we have exactly one odd number. So the question is, what's the probability? We don't want to know the probability of A or B. We want to know the probability of A or B. In other words, the first roll is even, which is A, or exactly one roll is odd. So this is the same thing as saying, what is the probability of A union B? All right, so first things first, why don't we, and now we've already done this part. Oh, we didn't, here's what we forgot to do. We forgot to define the intersection between A and B. So the only thing they seem to have in common is ZO. And so now we've got all three components of the addition rule. The probability of A, because all these elements are equally likely, we can simply write this as 2/4 or 1/2. Because remember, the entire sample space has 4 equally likely outcomes. Same thing with B.
Professor, the screen just went back to something that like the Zoom page, which you had before.
Oh crap. So what does that mean? You're seeing something?
Well, no, now it's gone. Now there's no sharing screen.
Oh, yeah, it's a complete disaster. Yeah, this has been going on all semester. I guess the Zoom product is not what it's supposed to be. And we're just going to have to put up with this. It's just somehow it doesn't quite make it through the whole session. And I don't know why, and I'm not a technology person. It's very frustrating, but I guess there's not much we can do about it. Anyway, so yes, so the A has a probability 2/4 or a half. B has a probability of 2/4 or a half. C, or sorry, not C, A intersect B has a probability of 1/4. Okay, so we're going to plug those into the addition rule, remember, which is okay. So now it's just a question of plugging in the numbers. And so there's, I've just repeated it here for you. So this is A, this is B, and this is the intersection, which is being subtracted. And that leaves us with a total probability of 3/4. All right, so that wasn't that hard. Now, as it turns out, there's another way we could have done this. Especially in cases where the amount of elements is not that large. What we could have done is just looked at the elements in these sets and said, well, listen, what elements belong to this union? Let's say that, let me make a list here somewhere. Remember, we defined A. Actually, I'll do this on a new slide. Oh, no, here it is, sorry. A, remember, was the elements EE and EO. B was the elements EO and OE. And so when you create a union from these, remember, you're looking for all the unique elements between the two of these. So in other words, they both have an EO in common. So this list represents all the unique elements between the two sets. And also, remember, we have all equally likely outcomes. So therefore, the probability of A union B can be easily calculated as the number of elements in A union B over the entire sample space, which is 3/4. So it's the same thing. It has to be. But in general, when your sets are larger, you might be better off. Which one you use ultimately will depend on what kind of information you have and also how large the sets are, because in some cases, one approach is quicker than the other. So it's good to know different ways of getting at the same results, because you never know when each approach will be a little quicker. So here, this might have been a little faster than using the rule, but maybe not. Like I said, it depends on what kind of information you have, but it's always good to have alternative ways of getting at the same results. It's no different than driving to school. It's good to know alternative ways of getting there, just in case there's, construction, or if trees are falling down, or if there's ice, or whatever the case may be. You know how Purchase is, there's a lot of trees along there, and every so often the wind gets going, and before you know it, there's trees down all over the place. And one of the entrances to the school can be blocked. And it happens, pretty much at least once or twice every winter. And so you need ideally to figure out how else to get in there, because otherwise you won't be able to get into the place at all. So having multiple paths of getting someplace is useful. And here, of course, multiple ways of getting to the same result is also very useful. Now, there's a special case, though, that we need to consider. If the addition rule is applied to two events that are mutually exclusive, then we can simplify the rule a little bit. So remember what it means to be mutually exclusive. It means they can't both be true at the same time. Or another way of thinking about it is that they have no elements in common. Like imagine, like I said once before, A is the odd numbers and B is the even numbers. Clearly they have no elements in common. There's no such thing as a number that's both even and odd. That makes them mutually exclusive. And of course their intersection is empty. And even more importantly, the probability of the empty set is 0. Okay, so the probability of this empty set is 0 because this empty set is what we call an impossible event. It would be like, imagine we flipped a coin. A is defined as a head and B is defined as a tail. Is it possible for the coin to be both heads and tails? No, obviously not. That can't happen. So that would be an impossible event. So if that's true, then our addition rule can be streamlined just a little bit. Okay, now let me show you why. Because the full rule is this. Oops. If A and B are mutually exclusive, meaning they can't both be true, then the probability of A and B is 0. And guess what? That means we just can drop it out from our addition rule. Think of this as the full addition rule or the general additional rule. This is now the special case. This is, we will call this the addition rule for mutually exclusive events. And it's only slightly simpler. It doesn't like save us a ton of time, but it's important to recognize that in that one particular case, then we simply add up the probabilities of A and B. We don't need to subtract this intersection because it simply has a probability of 0. All right. So let's go back to the die rolling experiment and look at a case where A and B are in fact mutually exclusive. And we'll apply this. So let's say this time that we have the following events. And remember, here's our sample space. And this one, the first roll is even, contains the events EE and EO. The second one contains OE and OO. And you can see that the two of them have no elements in common. They're said to be mutually exclusive. So if I need to know the probability of their union, I now can use the simplified addition rule. All right, so already I know that that's what I'm going to want to do. So the first thing we want to do is, besides identifying what these events are, let's calculate their probabilities. And this will be straightforward because again, we have all equally likely outcomes. So the probability of A could be thought of as simply 2 out of 4 or 1/2, and the probability of B can be thought of as 2/4 or 1/2. Okay, and that's what we have down here. Well, now what do we do? Well, the addition rule with mutually exclusive events tells us that all we have to do is add together the probabilities of A and B. And so let's do that. And it adds up to 1. Now you can tell it has to add up to 1 because those two events cover all the possibilities. Okay, remember A means the first roll is even. And the second one says that the first roll is odd. One of those has to be true. So an event whose probability equals 1 is said to be a certain event. And its probability is 1 because it's guaranteed to happen. In this case, we're guaranteed that the first roll is either an even or an odd. And therefore, that becomes a certain event whose probability must be 1. Okay, now the complement rule. Now the complement, the first thing we want to do is understand what it means for events to be complements. Now, here's a formal definition. I want to explain to you in a little more detail what this actually refers to. So you can see that formally we define complements as two events, A and B, where two things have to be true. Their union is the entire sample space, and their intersection is the empty set. Okay, so this implies that the probability of A union B is 1, and that the probability of A intersect B is 0. Now, you might say to yourself, well, how is this possible? All right, well, I'm going to give you a couple of fun examples, and you'll say, oh, I see what you mean. So let's start with a case of cards in a deck. Okay, so suppose an experiment consists of choosing a card from a deck. S would be the deck of cards. Okay, that's our sample space. And let's define A to be the card is red. Okay, I'm not going to write them all out, of course, because there's 26 of them. And B is the event that the card is black. Now, if you're not familiar with cards, a standard deck of cards has 52 cards, half of which are red and half of which are black. Okay. All right, I'll tell you what, let's throw in just a very brief tutorial here. A standard deck of cards contains 52 cards. These are divided into 4 suits: hearts, diamonds, spades, clubs. Hearts and diamonds are red. Spades and clubs are black. So already you can see half are the cards are red and half are black. But let's just take another dive into this. Each suit contains 13 cards. Each has its own unique rank, it's called. The ranks are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have the jack, the queen, and the king. Okay, so, all right, I know this may not have been necessary, but not every single person on the face of the earth is familiar with decks of cards. I mean, not that, maybe most people, but just about. There's always, I've had this happen several times in my classes where I start out assuming that everybody's intimately familiar with cards, and then almost without fail, somebody wasn't, knowledgeable about cards. So I want to make sure that doesn't happen. But really, all you have to know is the numbers of cards for these examples, which ones are, belong to which suit, and which ones are red, which ones are black. So anyway, with all that being said, there are 26. So we know that, let me just go back here. So we do know two things. First of all, there's no intersection between the red and the black cards. No card is both red and black. Okay. On the other hand, these add up to the entire sample space. Every card is either red or black. And because these are both true, that means A and B are complements. All right, so that's what it means to be. Oh my God, is everyone still there?
Yeah, we're here.
Oh, thank God, because all the crap is missing. I mean, I can't see any of the little signs that say that you're here or not here. All right, good. So these are complements because we have two sets of cards which do not overlap, and yet the entire deck consists of their union. So another example would be, for example, let's say white and black pieces on a chessboard. So even if you don't play chess, all you need to know is that there are white and black pieces. I mean, that's it. Each player gets the same pieces, only one side is white and one is black. And so every piece has to be one or the other, but there's no such thing as a piece that's both. There's another possibility. Another would be the fiction and nonfiction books in a library. Okay, they're all one or the other, and no book can be both. Okay, now sometimes you get supposedly nonfiction books that are really a fantasy, but no, it's either fiction or nonfiction. All right, so once we get that established, I think it's easier to think about complements in terms of these applications. It's fine to memorize these rules, but I think it's easier to remember what it actually means if you think about these examples like red and black, or white and black pieces on a chessboard, that type of thing. Or you know what, you can go crazy thinking about examples. How about all the lefties and the righties in a class? Assuming that there's no ambidextrous people, let's say, the left-handers and the right-handers, because you have to be one or the other, but you can't, well, okay, now that I think about it, that's a terrible example because you can be both. So let's scratch that example. What else could we do? I don't know. Oh, odds and evens, of course, odd numbers and even numbers, they would be complements. So anyway, notation-wise, we're often going to see this symbol C, which simply means a complement. All right, for whatever A is, its complement is going to be written as AC. Now, let me show you what the rule looks like. There's actually two equivalent ways of writing this rule. And you're going to be surprised how simple it is. You can write the probability A equals 1 minus the probability of A complement, or you can write the probability of A complement is equal to 1 minus the probability of A. They both represent the same information. All right, so that's the rule. Now, what I'd like to do, not today though, is show you why this is true before we do any of these examples. And then what's coming right after this is the multiplication rule. That one is a little bit more challenging. And that requires us to create a very useful example so you can see what this is all about before we dive into the actual math. So those are all going to be very time consuming. And since we got cheated out of watching our video, one of our videos, I think we can probably stop here and pick it up next time. Hopefully I'll have Zoom fixed by then. And so we'll stop here. Now remember, you're supposed to have your second midterm ready by tonight if it's not already done. And then we'll just carry on with 11. And at some point, we'll have some problem sets. And then after that comes 12, which is our introduction to statistics. And then when that's done, we're pretty much done with the course. But that's probably going to take a few more weeks, especially considering that we do have Thanksgiving vacation coming up. So we're moving along pretty well. And I'm hoping that you're finding this interesting, especially when you see a video like the one with the birthdays. You can see that combinatorics can actually be a lot of fun, when applied to interesting areas. So we'll try to keep going with the discussion, but also I do have, like I said, some more fun videos that we can look at to help us bring this stuff down to earth and understand some of the many things that it could be used for. All right, so now, of course, we know that the Zoom is completely screwed up, so we'll just stop right here. Once you log off, I don't know what's going to happen. Maybe it'll turn itself off automatically, but I'll have to see what I can do here. So, all right, I guess we'll just see you all next time.
I have a quick question.
Oh, sure, go ahead.
All right, so I already handed in the midterm because I thought it was due at 10:30, but now I have time to fix one of the answers. So can you pull it up just so you know what I'm talking about for question 2A? Am I allowed to ask you something? Because the wording is kind of.
Oh, all right, I'll tell you what. I will go find the exam.
It's just a question about the wording. This is the
Oh,
only.
no, absolutely, yes. You should ask questions about the wording because it's not, it's challenging to write word problems because I think I'm making sense and maybe I'm not. So if you're not sure, you always can ask. Let me just grab it here.
Yeah.
Yeah, because this is not meant to be an English test or something like that.
Oh, yeah.
You know what I mean? It's just, do you understand the math? That's what we care about here. Whoops, that's the wrong one. So the writing is not meant to be an impediment. It's, all right. So number 2, you said is giving you a problem. Eileen?
Yeah, sorry. Okay, so it says for 2A, it says
Mhm.
how much total interest will she pay?
Mhm.
So when it asks for the total interest, does it mean that it wants the interest being paid plus the initial 40K, or does it just want the interest that's added up on top
Oh,
of the 40K?
okay. Here's what you're going to do. Once you figure out the total amount she has to pay for this loan, you take that total and subtract the principal that she borrowed, which is 40,000, and what's left over is your total interest. So let's say that she ends up spending $50,000 on this loan. The last $10,000 would be your total interest.
Okay, perfect. I think that's what I did on mine originally.
Okay, good. Yeah, that's all it means.
Okay, awesome. Thank you.
Right? Okay, good. Is that the only one?
No, yeah, that was it.
All right, perfect. Anyone else? I can't tell if you're still there or not. So if there's nobody else, I'm just gonna, like I said, I can't even tell if you're here or not. So this is so bad. But all right, I'm gonna assume that everybody's done and I'll see you all next time.
All right, take care.
Okay, bye. Oh, what happened here? Somehow it has returned.